We've created an interactive children's exhibit using machine learning. My name is Jewel, and my group members are Jonathan and Precious, and our advisor is Jennifer. Just a little bit of background information. We're all majoring in mechanical engineering at Leeward Community College. So we've created an interactive children's exhibit where children can use physical objects to interact with a virtual environment. Especially with our current situation of having distance learning, we wanted children to still experience what it would be like to be in that exhibit. A virtual environment can demonstrate learning concepts when a physical environment is too dangerous or too costly. For example, we've created an undersea exhibit to show proof of concept. And a few of our objectives are to identify the type of object that the children are holding, which will be triangles and stars. Then it will identify the type of location the object is and have the fish react to the object appropriately.
So like Jules said, we wanted to make an interactive virtual experience with our project. We created a virtual ocean scene with animated fish that can swim around and react to physical objects. The video on the top right shows our fish swimming across the screen. To create our exhibit, we wanted to use transfer learning to retrain an existing neural network to identify new objects that we create. We decided to use the VGG16 object classification model, which we got from the PyTorch library, and we retrained it to recognize stars and triangles. We then wanted to get live video feed from the webcam as input for our new model to classify the shapes that we hold in front of the camera. Finally, we wanted our animated fish to react to the shapes in real time. The picture on the bottom right is an example of how our exhibit could be set up in a classroom. The scene is projected onto a screen, and the child interacts with it by holding a shape in front of the camera.
For materials, we've used the Unity game engine, Jupyter Notebook Python editor, Spider Python editor, a pre-trained object detection model, VGG16, Visual Studio C# editor, a web camera, a video projector, PyTorch library, and a OpenCV library. For the camera, it will view the object, virtual scene, and the child. Then the TPU uses a pre-trained neural network to determine the type of object, which will then go to the data collection system where it will determine the location and type of physical object that the child is holding. Then returns the bounding box and object classification, which will finally go to the Unity server, which will create the virtual environment and react to the physical object.
For the machine learning portion of our project, you can see the architecture of the VGG16 model that we used in the diagram on the right. First, we created a data set with images of triangles and stars in front of our virtual scene. Then, we used those images to retrain the VGG16 model to identify those two shapes. For retraining, we focused only on the portion of the model on the very right of the diagram that is in green. This is the final classification layer of the model, and we changed it to reflect our desired output. Now, instead of the 1,000 classes that the original model is trained to recognize, the output for our retrained model will show the probabilities for two classes, triangle and star. These probabilities are used to predict which shape is present in the picture. After we retrained the model, we used OpenCV to access the computer's webcam so we could identify stars and triangles on camera in real time. For the virtual environment, we created a virtual scene with a coral reef background and 4 different kinds of fish. Then we used C# scripts to animate different fish behaviors. For networking, we decided that running the model and game engine on separate computers would allow us to process the input and generate a reaction quicker than if we ran the entire thing on one computer. So we used one computer as a tensor processing unit to run images through our model and send classification results to a separate computer, which runs our virtual game engine and animates our virtual scene. Running it on separate computers like this would also allow us to add more cameras and TPUs in the future to create a larger, more immersive exhibit. The program is broken up into two main processes, each on a separate GPU to minimize load on the processors. The tensor processing, or machine learning, is done on an NVIDIA graphics card running CUDA. First, we begin a thread which will asynchronously transmit the state data. This way, the system can send the last found object classification upon request without disturbing the tensor processing. Then we read a single frame from the camera, process the image so that it is formatted and sized properly for the tensor, then apply the VGG16 tensors we have retrained. The output of the retrained VGG16 model is a tensor indicating the probability of each class. We find the top class, or top K, and if the class has a probability of greater than 60%, then the model has identified an object in the image. Otherwise, the model is reporting that there is no object in the image. If there is an object in the image, we check to see if it is a triangle. If it's not a triangle, we report that it is a star. The virtual environment requests state data from the TPU every frame. If the state is 0, the fish will exhibit default behavior where they drift randomly. If the state is 1, it found a triangle, and the fish will move out of the scene quickly. If the state is 2, then there's a star, and the fish will move into the scene quickly.
For transfer learning, we were able to retrain the VGG16 model to correctly identify triangles and stars with a greater than 70% probability. The retrained model was then saved so that it can be used without having to retrain every time. We also were able to get the images taken from the webcam. For networking, we were able to send and receive data from the TPU to game engine. And for Unity, we were able to use different behaviors for the fishes using a single script. To the images on the right, you can see our Unity screens. For the default behavior, the fish would drift in a random direction slowly. For the avoid behavior, the fish would move quickly to the nearest horizontal edge and exit the scene. And for the attract behavior, the fish would either move quickly into the scene if it wasn't already in the scene, or it'll do nothing if it was already in the scene. In the first video, we can see the fishes avoiding a triangle object. In the second video, we can see the fishes attracted to a star object. Figure 1 and 2 showcases a greater than 75% probability that the image contains a triangle or star. Figure 3 shows a roughly 50-50 probability for either a star or a triangle, implying that the image contains neither shape. And for figure 4, we trained our model using 209 images, and during training, our model was trained so that it had an accuracy of 99% for star and 95% for triangle. 12 additional images were taken, and these images were not used to train the model, but they yielded 100% accuracy.
Some of the key results from our project was that we were able to use transfer learning to retrain the VGG16 model to recognize stars and triangles. Our model can easily be retrained with other images like coral or seaweed to add more objects and interactions to our exhibit and make it more educational. Finally, because we were able to use a modular setup, we can also add more cameras and tensor processing units to expand the exhibit. In the future, we would like to modify our classification model so that it not only identifies the object on camera, but also detects its location in the scene to make the exhibit more interactive. We would also like to add more cameras, projectors, and TPU modules to make the exhibit more immersive so it can cover an entire room instead of just one section of a wall. Here's a list of our references. And thank you for listening.